Thank you all for being here and joining us for this panel on quantum sensing at scale, navigating commercialization roadblocks. And I'll be the moderator, so I'm Constanza Vidal Bustamante. I'm a fellow with the Center for New American Security, or CNAS. We are a think tank in Washington, D.C. We focus on national security policy broadly across various different programs, and I'm specifically with the Technology and National Security Program, where we focus on critical and emerging technologies, AI, biotech, cyber, and quantum. And I'm specifically focused on quantum technologies and their intersection with national security. And I enjoyed very much over the past year doing in-depth research and culminating in a research report that I recently published a couple months ago on quantum sensing. And I think to me it was a privilege to learn about the status of this technology that gets less attention than quantum computing in the media and certainly in investment cycles, but certainly has many near-term applications. And I think for me specifically, being a think tanker thinking about national security, it has many applications for defense contexts, for position navigation and timing, for various others that we care about from a national security perspective, and that really could get us to a point where we can commercialize and see the value of those technologies that can then have economic and security impacts, but I think importantly, from a policymaking perspective as well, they can accelerate applications in other domains of quantum sensing, but also even quantum computing. And I think we'll touch on some of these themes during the panel today, and I'm very grateful to have our panelists here joining us from Q Control. So we have Aravind Ratnam, who's the Chief Strategy Officer for Q Control. We have then to his side Sristy Agrawal, who's the co-founder and CEO of Mesa Quantum. And then finally we have Matt Kinsella joining us from Inflection. He's the CEO there. So I wanted to get us started by kind of providing some background for the folks here. I think, like I said before, most people have heard about quantum computing a lot, and certainly in the news cycle much more frequently than sensing. And they might not be aware of the wide variety of quantum sensors that exist. And I think we have a really good representation of various varieties of quantum sensors, and also various different applications that you might be working on for the near term, and perhaps thinking ahead a few years out. So I wanted us to get us started. Maybe we'll go in order. If you could tell us a few about the sensors that you're working on and applications that you're focused on, and kind of what is the promise of those sensors that you're working towards, before we get into the details of like timelines and bottlenecks that you're facing. But what are you working on, and what is it good for, and why is it better than a classical alternative? So we'll start with you.
Okay, cool, thanks. Q Control, we are working on quantum sensors that do magnetometry, specifically for magnetic navigation, typically for airborne applications. We also work on gravimeters for seaborne applications. And just 101, quantum sensors have the inherent advantage over classical sensors that their error is bounded, whereas classical sensors suffer from drift, and that tends to increase indefinitely with time. Quantum sensors can, because they use atomic effect, they tend to bound the amount of error. And at the field level, whether it's planes or ships or submarines or any of the drones or whatever it is, what this means is that you can navigate for a very long period of time while having the confidence that you're not off from the real position by, or you're significantly off from, you're significantly close to exactly where you think you should be. And when you talk about ships and submarines, you're talking about almost being able to outlast a war. And so that's really transformational. So in terms of timing, the need is today, and in terms of the technology, it is today. And so it has turned from a science problem into an engineering problem. How fast can you make it?
Yeah, we Mesa Quantum. We focus on chip-scale quantum sensing. And so we've had atomic clocks for a while. That's how GPS works. It's essentially large atomic clocks on a satellite. But GPS is not resilient, and we have been looking for alternative technology, primarily around timing, because that's one of the biggest contributions, economic contributors of GPS. Now, classically, there have been systems which perform as well as our systems do. Like, we are focused on the chip scale domain. The challenge is that those systems are much larger. They consume a lot more power, so they can't be used for the kind of applications that we are going after. So quantum sensing can either be, as Aravind talked about, it can really push performance and demonstrate something that's never been done before. Or on the other side of it, it can allow us to have great performance, which with classical systems required much higher swap, so much higher size, weight, and power. And with quantum systems, you can really miniaturize them and have them everywhere. So we expect our systems to be in autonomous cars to be able to detect spoofing, in drone systems, swarm drone technologies. But then we also expect them to be, in infrastructure, in our everyday infrastructure, where you don't want something very large, very bulky, but you want them everywhere to provide that resilience. So that's what we are focused on.
Totally agree with everything that Sristy and Aravind said, and Constanza, thank you for hosting us. This is great, and thanks for everybody for being here. I don't disagree with anything that's been said, so maybe I'll just tell you a little bit about Inflection and where we're focused in the quantum sensing world. So Inflection's a pioneer in the neutral atom quantum modality. And the nice thing about neutral atoms is it's a very flexible modality. It can be used to do a lot of different things. And so on one hand, you can build quantum computers with neutral atoms, and the growth in qubit counts and the growth in the quality of those qubits has been pretty shocking over the last 5 years in neutral atoms. But neutral atoms can also be used for a range of sensing applications. And so the way I've always thought about Inflection, and I was the first investor in the company going back to 2018, is that you can take this very flexible quantum modality and you can point it at a few different applications. And those applications are largely under that broader sensing umbrella. And so we've talked about timekeeping, and timekeeping, couldn't agree more with Sristy that the GPS system is a position navigation timing system, but in reality it's a lowercase p, lowercase n, capital T. The time is really the most important service, and a lot of the other things we use it for, navigation, et cetera, are sort of derivatives of that timestamp. But in addition to navigation, it's used to synchronize the electricity grid, synchronize the RF network, synchronize financial markets, synchronize data centers. And if you lose connectivity to the GPS system from just the timing perspective alone, it's a total disaster from a critical infrastructure perspective, let alone the implications in any kind of hot war where you can almost be certain there would be no GPS available. So the side that is able to navigate without that access to GPS would have a huge tactile advantage. So timekeeping is one of those areas where you can point neutral atom technology at, and we make clocks like Sristy was saying. They aren't chip scale yet, but they're the size of a VCR, call it, and those are optical clocks that used to be the size of a table. And so this is very, very high performant picosecond level synchronization, which is the synchronization levels you would need to, say, intercept a hypersonic missile that was coming at Earth as part of the Golden Dome is a good example. Simply put, greater synchronization gives you greater clarity in a radar system. You can also use neutral atoms to build antennas, and that's another broad bucket of the quantum sensing. That's a bucket of the broader quantum sensing umbrella. So the same way you can turn atoms into the ticking of a clock, you can turn atoms into antennas. And these antennas do things that no classical antenna can do, and kind of turns on its head all of the last 120 years of what we know about RF technology, where you have to use a physical aperture like a metallic antenna to receive a radio wave, right? And what we do is we turn these atoms into antennas that can receive the entire electromagnetic spectrum, completely breaking the correlation between the length of the wavelength that you're receiving and the size of the antenna aperture. So normally, to receive very low frequency, long wavelengths, you need antennas that are massive, in some cases up to 1 kilometer long. Those can be shrunk to the size of a sugar cube. And then finally, you can use neutral atoms for some of the inertial sensing work that Aravind was talking about. And in particular, we've focused it mostly on gravimeters, which we've sent up into space. The technology's been up in the International Space Station since 2018, and working with NASA to send more of this equipment up into space. And what can you do with a gravimeter? You can actually sense with great precision the changing of the gravitational forces on Earth's surface and the things that impact that, like the melting of polar ice caps or the depletion of aquifers, or in some cases the creation of tunnels underground or the movement of nuclear materials which carry a very heavy mass. So we're focused on a number of different quantum sensing applications, all brought about by neutral atoms.
Great. So we heard a wide variety of sensors and applications for them. I think the next natural question is to ask then, where are we in that kind of vision for where these sensors will go and what they will be able to do for us? So if you could give us a quick update on what is the current status of the sensors you're working on today in terms of both performance and what kind of sensitivity they can reach and so on compared to existing alternatives, and also in terms of size, weight, and power. I think some of you alluded to this, right? That's an important component of the technology maturation levels for these technologies. So where are you right now? And maybe if you can anticipate where we will be maybe 3 years from now in terms of where these sensors will be.
I'll go first because I have the microphone. I'll be quick because I spoke for much longer than everyone else last time. So on our clocks, I sort of told you the size where it is today. It's about the size. It's like a 3U rack mount, so call it 3 pizza boxes or so. But if you open up those pizza boxes, it's a lot of lasers and a lot of wires jammed in there. So those can all be integrated down, and so that's what we're in the process of doing. It'll be 1U in the not too distant future. And then ultimately, because really everything we do in neutral atoms is based on photonics, these can all be integrated down to photonic integrated circuits. So it will be approaching something along the line of chip scale over the long arc of time, call it 3 to 5 years. But right now, I think 3U, 1U, and then approaching chip scale over time. And the performance level is really only been able to be had in those refrigerator to room size technologies. These are optical clocks, and so picosecond level precision, which again had only really been possible in room size technologies historically. The size and weight of the QRF devices I was telling you about, that's about the size of a mini fridge today, and that's all just the photonics and electronic systems. We haven't really spent much time integrating those. The aperture itself is the size of a sugar cube, but the photonic system is a mini fridge. It'll be the size of Ticker, 3 pizza boxes in the not too distant future. And then the inertial sensing equipment is bigger, but of course big enough to be sent up into space, which we've done. So that's where we are from a size, weight, and power as well as a precision level.
Yeah, for us, we're working towards the final optimization. So it's a bit bigger than a golf ball, but we plan to be deploying early next year. And so the largest offering we would have would be a golf ball sized device. Its performance is like, in terms of AREV, it's like 10 to the minus 12, which in the chip scale domain is exceptionally high. And then our goal is to have a blueberry-sized device as we move towards like more and more chip scale. So that we expect to be in 2027. So we've active efforts moving towards that direction, but just requires a lot more capital optimization. And so that's what we are doing right now.
Yeah, the general theme that you'll hear is faster, smaller, cheaper, which is what you would expect. For us, since we're focused in navigation. For us, the first thing is, we are already at TRL 6-ish, sort of moving to 7, 8, 9. So, anything that goes on a commercial airliner or for defense applications needs to be certified. So we are focused on our manufacturing strategy, and then working actively with our partners. That's the first thing. The second thing is it's not so much the form factor because our sensors are already small enough. They just need to be certified. So the second leg is really about aerospace grade certification, and we are moving in that general direction. And then the third thing is ensuring that we are able to hit all the platforms of interest to us. Whether they're Class 2 drones or above, commercial airliners. We're going to soon test on an Airbus A350 because they're an investor and a customer as well. We're working with Lockheed Martin. Thanks, Danny, for being here. And yeah, so ensuring that we are on the helicopter platform, that we've been contracted with DARPA. The last thing that we're going to do, so everything that you've heard so far has sounded like engineering. The only sciencey stuff that I'm going to publicly talk about is because DARPA has contracted us to work on robust quantum sensors that are next generation, and Lockheed's going to be part of that effort too. Is if you look at quantum sensors that are deployed in the field for navigation, they have a bunch of band-aids, right? You put them on a boom so that you're away from the electromagnetic noise of the aircraft. Sometimes you have them have them be gyro stabilized so that you're guarding them against vibration and harshness, etc. So we want to do away with all those band-aids and essentially make incredibly robust sensors that using the principles of physics and then stabilizing them right at the chip scale level so that whatever goes into the warfighter and as well as for commercial applications in the next generation is not dependent on any of those band-aids. So yeah, for us, generally speaking, it's manufacturing, it's certification, and number three, coming up with the next generation sensors that can fly in the air for decades.
Yeah, great, and I think that's a great segue to my next question. So, when you look at private investment in quantum, the large majority of that, about 80%, goes to quantum computing companies, and quantum sensing, according to some data that I've looked at, is about 8% or so. So in that environment, public capital, public investments ends up being quite important. And all three of you were just talking about DARPA, have benefited from defense contracts, both from the Department of Defense here in the US and some internationally as well. So I was curious to hear how you have benefited from those contracts and that kind of sustained investment in accelerating your technologies. And are you optimistic that these programs will lead not just to kind of R&D investments and support, but actual procurement and adoption and integration into defense platforms in the next few years? Matt, do you want to start maybe with this one?
Yeah, absolutely. Those types of programs are absolutely critical, especially for small companies like we were before and still are in many ways, that those help get those technologies off the ground. And what I found so interesting, and maybe we can track the process of our clock as an example of maybe how this can go soup to nuts. And so back in 2020 or so, DARPA put out a program asking, could you take this table size optical clock and could you shrink it down to something the size of a 3U rack mounted, again, like 3 pizza boxes stacked on top of each other, which at the time seemed almost impossible. But we won that contract and we were able to do it, and that gave us our prototype that we call Ticker. And the great thing about that is there is a demand for that product. Somebody wanted that product, otherwise they wouldn't have put that call out. So not only is it funding, it's a bit of a early view as to what product market fit might look like, and then an embedded potential customer. And so you get a prototype after that process, and then you have a hunch that somebody wants this in greater volumes at some point in time, and then you can move on to some of the more streamlined procurement processes that the government's put into place. What we utilized for the clock was called the AppFit program, the Accelerated Procurement for the Fielding of Innovative Technologies. And that was an $11 million contract, which basically is more funding to make the manufacturing process more robust, but also an actual procurement order of the clocks to start that ball rolling. And so we've benefited greatly from those types of partnerships. And I often think about all of our products as a conveyor belt. And on the left-hand side of that conveyor belt, you have a DARPA program or a NASA program or something like that. And then as you move down that conveyor belt, you move more towards the commercialized mass market opportunity. But it all starts with those types of programs. So incredibly beneficial to Inflection, at least.
Yeah, very similar for us. So we're much earlier stage compared to Q-Control or Inflection, but even for us, right, we raised our venture round last year and we got just as much in government contracts. And the two things it does, firstly, it sends a very strong market signal, especially to investors, as you mentioned, like that ecosystem is still maturing. So this shows them that there is an appetite from the government. But then it also helped us engage quite a bit. So we got funding through alt PNT, so trying to imagine what alternative to GPS architecture would look like. And it got connected us to all the right stakeholders, not just with Space Force, who led this funding, but across SOCOM, Air Force. So, because once you're plugged in, you start getting more and more connected. So, yeah, it's been super, super valuable for sure.
For us, there's really three tenets to our investment strategy as far as sensing is concerned. The first one is, of course, government contracts. Typically, it's government contracts that help you sort of get off the ground, but it's kind of dangerous to rely on them in the long term. The second leg, and that also includes working with defense primes and supplying into the warfighter, as I mentioned. Our second leg has been, we've been fortunate to be supported extensively by Airbus. And we're talking to a lot of commercial airliners, right? Because at the end of the day, airliners are the first ones who are suffering from loss of GPS, and every airline CTO is interested, right? And there are some that are more innovative, some that tend to wait until they absolutely need it. And so we are talking to a number of airlines, and ultimately it'll be them who will help fund the program. And then the last piece of it is, we are a larger private company, but we are choosing to stay private. And we are interested in talking to investors who understand defense fundamentally, and also who generally understand dual use of, and not all investors appreciate it, but what's happened in the last 2 to 3 years is, you're starting to see the journey that Palantir went through and Anduril went through, and there's Shield AI. There's a number of companies out there that are neo-defense, so to speak, that are infusing software and AI with traditional defense hardware, and the investors who understand how that is evolving, how that landscape is evolving, are those who are typically interested in Q control. So we're addressing all three.
Great, and I think you anticipated my follow-up question, so maybe I'll ask the other two panelists to chime in. But like you said, right, the defense contracts have been really helpful, but can only get you so far, and you need a more sustainable, broader market in civilian applications, commercial side. So curious to hear how we heard a little bit from you on your partnership with Airbus, but how else you're building that ecosystem and that market that to go beyond the defense contracts and to make it more sustainable over time. And if you have found any partnerships, like the Airbus example, particularly helpful in bringing the quantum sensing applications beyond the defense ones.
You want me to go, or?
You can, if you want, yeah. If you want to expand on what you said on Airbus.
I'll just say very briefly that, look, after we released this product called Ironstone Opal that did public demonstrations of GPS-denied navigation. We had interest from all kinds of people, boat operators who are seeing loss of GPS, to a number of players that I can't really name yet, but in general, there's a ton of interest from and then I'll also mention that shipping operators typically are ones who tend to get hit by loss of GPS. So there's tremendous interest there. In general, I think looking long term, the sensing market for us is going to be 50-50 between commercial and aerospace and defense.
Yeah, even for us, defense is a very exciting space to start with, but there's, even with pilot testing, I think 60% of our customers are not from defense. So the way we think about our market is in 3 segments. The first is where you don't have access to GPS, but you need precision timing. So, of course, defense is a major factor there, but also underwater, because GPS signals are electromagnetic, so they disintegrate inside. Which makes any sort of navigation, sensing, communication extremely difficult. And when you're operating in remote environments, you're very aware of how much battery packs, the size of the battery packs you want to carry for your mission. So having something low swap is just non-negotiable. So that's one segment. The other segment is GPS resilience, where you have access to GPS, but you don't want to be relying on it completely. Because it can be catastrophic if it goes down. So network infrastructure, where you don't need this in your master clocks, but across nodes, where you have lower swap requirements. And the third is just the complementary, where you have access to GPS, but having these devices actually enhance your performance. They are known to help you navigate with less number of satellites. They are known to help you have better vertical resolution. So this is not just autonomous defense equipment, but it's also autonomous robots that we will come up with. It's also autonomous cars and autonomous drone delivery systems. So we do see a strong commercial side of it across all these three segments. Like with underwater, it's oil and gas. Oil and gas has a massive market. They deploy hundreds, sometimes even thousands of nodes in a single operation, requiring as many clocks with each node. So
the only thing I'd add is we all have the benefit of all of our products being very dual use. And that would be different than an Anduril or Palantir is dual use, but Shield AI. And so that is a great thing because it allows us to address the commercial market opportunity, not just the defense market. The way I think about those different customer bases is right now for the precision level that quantum can provide, a lot of the demand comes from the broader national security umbrella. And I'd put aerospace in there as well because they're worried about GPS denial. Over time, we'll see much more demand coming from the commercial markets. But what's going to have to stimulate that is volumes, because volumes will help us drive down the costs. It'll help us drive down the size, weight, and power, and it will help us ultimately make these much more manufacturable. And so we at Inflection, and really all of us up here, are heavily focused on the defense industry or that broader national security umbrella. Because for lack of a better term, that's where the dogs are eating the dog food today. And we can feed that dog food to the dogs and drive up volumes and drive down costs and then address the much broader commercial market opportunities that we'll find in data centers, in the RF networks, et cetera. And so that's the strategy I think all of us are pursuing for the most part. And we just need to get those TRL and the more probably for the max technology readiness levels, but the manufacturing readiness levels higher to appropriately address the commercial markets where they're utilizing very, very robust, good technology. It's just we can perform those things better by orders of magnitude that just need to be more cost comparative.
Great. And I think you were talking about volumes and kind of what it takes, thinking about what it takes to get there. And I think one of the main findings that I shared in my report as to challenges for quantum sensors to move forward is that we have a fairly thin supplier base for key materials and components, advanced photonic fabrication facilities, and so on. So can you guys reflect a bit on how fragile the quantum supply chain is today? And maybe, Q-Control, Inflection, you guys have operations across multiple countries. Mm-hmm. Maybe how are you using that to fill some of those gaps and address those challenges and keep you on track to develop your technologies?
You're right, Constanza. The supply chain, specifically the photonic supply chain, is an area that we spend a lot of time thinking about. And one of the solutions is to have some redundancy across geographic borders. And so we are creating the ability to build our clocks entirely in the UK in a sovereign way. So an entire supply chain there in the UK. We may create that capability in Australia. That also allows us to supply some of those components to the US if we need them here as well. And so that is something we spend, again, a lot of time thinking about, and something that will need to become very robust as we start to think about ramping up the volumes to the levels we were just talking about to address the commercial use. So all I can say is I totally agree with what you said.
So supply chain's been definitely a very critical issue for us, especially since we're chip scale. Volume is where our company sits. So quantum's kind of in that interesting cycle where components are mature, but the demand isn't enough for them to be produced at scale. So it's not profitable for entities who are doing it. And once those entities get acquired, the quantum part of it often gets gutted. So you see that gap in supply chain happen constantly. When we started out, we did not plan to work on the components at all. But within a few months, we realized that if we wanted to make sure that we can provide reasonable lead times and we can actually deliver to our customers, we had to vertically get integrated. So we personally started looking into different components from lasers to nanophotonics across the stack, and we started innovating on it. In that process, we realized that's not something you can do on your own. It's a community play, right? The things that we were building was relevant not just for us, but other quantum sensing companies, even quantum computing companies. So we started collaborating with them. So we're in that niche space where we're trying to build, we are working towards our full prototype for the clocks, but then we're also really trying to address the supply chain challenge for us and other companies in the ecosystem.
Yeah, I mean, I'll just comment that we live in an interesting time of geopolitical tension. And whether we like it or not, the U.S. lost a lot of its leadership in manufacturing, almost decades ago. And the thing is, as we enter this new reality, supply chains and becoming resilient is very, very important. And obviously, if you're set up in the U.S. and you're making for the U.S., you're obviously export controlled, and there's ITAR restrictions, etc. So far we are Australian and we are largely ITAR free, but we will have U.S.-based variants, and then securing that supply chain to make sure that critical components like lasers can be procured with high quality is of paramount importance to us. And as Matt was saying earlier, ultimately what's going to drive down cost and increase quality is orders, right? You are going to have to get orders, and then the government plays a very large role here, because when you can stand up those assembly lines. I mean, take example of microelectronics, or if you go talk to a fab or foundry. In order for them to have a dedicated line for you, they're going to have a certain critical order size, and you're only going to get that. Where will you find the money from, right? If you don't have that order from end customers, you're going to struggle to come up with the money, and at best you may have some human assembled R&D thing that's not going to scale in the long run, right? I remember a conversation I was having with TSMC in one of the LiDAR companies that I'd worked with, and for them, because autonomous driving had not really taken off, they were not willing to dedicate any amount of effort to it, and we struggled, right? And you're going to probably see some of this as well, but luckily, because it's GPS, GPS denied navigation is much more a painkiller than a vitamin. The need is critical, and the money is going to come. So we will be resilient supply chain wise. So lots of considerations there.
Yeah, great. And I think this came up. I think, Sristy, you mentioned this earlier in terms of some of these supply chain issues are kind of common across the quantum supply chain, not necessarily just sensing, and some of those are very much shared with computing as well. So I wonder to what degree you're tapping on those synergies and working across, you mentioned, Sristy, working with others in the ecosystem that could be seen as your competitors, but also because they have those same shared challenges, it kind of benefits all of you if you have a resilient supply chain, right? So how are you finding those synergies? And I think, Matt, you're in a special position here too, where you work on computing and sensing within the same company. So how are you tapping on those overlapping needs?
I don't mean to interrupt, but 2 minutes.
2 minutes, okay.
Yeah, 2 minutes.
I can briefly address that. So for us, we see that the ecosystem will rise together. We are very early. Of course, we are competing, but we are very early in this game. And there won't be any one single winner. So just enabling each other as we go through this, because again, if we won't have enough volumes to just have full fabs for us. But if you're working with other customers and other partners, then we would. So I think it's going to be a rising tide. I don't know what it's called. Rising tide rises all. Lifts all. Yes. So that's how we see this at least play out.
I do believe that if you look to the future, there will be more standards put around which, colors of light you use for various applications, and that will help to drive more volumes to the providers of those types of photonics who bring those colors of light. And so we can start to standardize somewhat to accomplish what we all talked about. There needs to be demand for it to be economically rational for people to invest in the photonic manufacturing ability to bring these things out in volume. So I think that's one thing we'll be driving towards as an industry, and that does require collaboration. From our perspective, the great news is that a lot of the different products we build utilize similar types of photonics, and so therefore we have a lot of leverage across the portfolio, and we use that to our advantage as much as we can.
Great. So I know we have maybe 60 seconds left, so maybe we can do a rapid fire, and maybe if you want to share, project into 1 year from now, what milestones do you expect to hit in your respective technologies that maybe you're excited about and looking forward to?
I am excited about selling a heck of a lot more sensors across clocks and QRF, and then hopefully putting some more of those sensors up into space, which would be really exciting.
I'm excited to have our pilot testing done by this time, hopefully, and starting to sell to our customers across. We are pre-revenue, like not grants, but we're pre-revenue now, so it's going to be very exciting.
5 field trials and more progress into programs of record.
It's quite exciting. Well, thank you all for sharing that, and thank you all for your attention.